Okay, in Unit 5 we're talking about statistics and probability. You did a smaller version of this unit last year in geometry. It was a little bit more simple. Now this year we're going to take the same concepts, we're going to make them a little bit more complicated, we're going to build on them, and then later in the unit we're going to get into some new stuff, some more advanced applications of stats. But first we need to talk about the fundamental counting principle, and we're going to revisit this in a second. But if you read this, right, number 1, the ice cream shop offers a choice of 3 different cones, 15 flavors, and 8 toppings. How many different cones can you build if you only get to pick one of each? Well, how would I approach a problem like this? So what we could do is build a different problem and do something like this. This is a simpler version of that problem with smaller numbers. Sandwich shop lets you create your own sandwich combos. Customers can order different kinds of bread, different kinds of cheese, and different kinds of meats. If you only get to pick one, how many different sandwich combos can you make? Well, we're gonna build a tree here. So what we've done, or at least what I've done, because you're not here, I've built a sandwich tree. I said, okay, I'm gonna make a sandwich. What's the first choice? What kind of bread do I want? Do I want white bread or rye bread? Everything starts from there. Then, okay, let's say I picked white bread. Now, what kind of cheese do I want? Do I want Swiss or do I want provolone? Okay, let's say I decided I want Swiss. I want white and then Swiss. My last choice, what kind of meat do I want? Ham, turkey, or roast beef? So here's my options, ham, turkey, or roast beef. So I can build a sandwich by saying I want white bread with Swiss and turkey. And that's one outcome. That is one sandwich I can make. All of these different endpoints here that I've circled represent different sandwich combos, whether it's rye bread, Swiss, and roast beef, or white, provolone, and ham. Okay, that's how we build. So how many circles do we have? I believe there's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can build 12 different combos. So that's one way to do this. It's certainly a way to, with a small problem like this, it's not that bad. It takes a little bit of time, but this shows every outcome that we could do. But if we go back to that example number 1, there was a lot more options here. 3 cones, 15 flavors, and 8 toppings. You wouldn't want to build a tree for something with that many numbers. So we have to find a simpler way. The fundamental counting principle lets us do that. If decision M can be made M ways and decision N can be made N ways, I can find however many different choices I have by multiplying that together. M times N. Okay? So let's take a look back at the example and see if that makes sense. I can choose from bread 2 different ways. I have 2 breads. I can choose 2 different cheeses, and I can choose 3 different, 2. And I can choose 3 different meats. Okay, well, those are all the different ways I can choose. The fundamental counting principle says if I multiply these things together, that will give me my outcomes. 2 times 2 times 3, that's 12. Okay, so that's how this works. So back to the very complicated example, well, at least complicated in terms of if I had to make a tree for it. It says I got 3 cones, 15 flavors, and 8 toppings. If I multiply that all together, I should get 360 different combos. You would not want to build a tree that has 360 different branches. One year, actually, I remember if you're going to Cold Stone is insane. It's expensive, but they have all of these different things. They have all these flavors and all these cones and then all these chocolate dipped cones. You can get a bowl or all this stuff, and then you that's before you even get to the fruits and the candies and the different toppings and stuff. We sat down on the website and we were like, okay, how many different types of cones can you have? How many different types of ice cream? How many different types of toppings? And for just one of each, we did the math to figure it out, and it was hundreds or thousands or something. And then that's not even getting into the world of you picking 2 candies or 2 fruits or a fruit and a candy, or maybe Cold Stone's crazy, man. Virginia license plates consist of 3 letters followed by 4 digits. How many different license plates can you make in Virginia? All right, well, you have to think about choices here. It told you in number 1, you only have 3 cone sizes. It's gonna be 3 letters. How many different letters can you choose from? 26 letters in the alphabet, and you have to pick that 3 times. It can be A, and A, B, right? And then it says followed by 4 digits. Well, how many digits can be in a 1 slot, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, but then 0 as well. So there's 10. 4 digits. Digit number 1, 2, 3, and 4. So I got 3 letter options and 4 digit options. Multiply all of that together and you get how many different combos you can have, which is an astronomically big number. That is a lot of license plates. And that took me all of, I had the answer, but you put that in a calculator, you can probably get it just as fast. That is way faster than doing that by hand. If you did that by hand, I think it would take you a year to build a tree with that. Science test is section with 12 true or false. How many different ways can Nick answer these questions? Well, how many different ways can you answer a true or false question? 2. There's only 2 of them. And I can do that. 12 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if I multiply all those 2's together, I would get 4,096. That's a lot of ways to do that, and that's also a long way to write that out. A simpler way would be to use exponents. Remember our exponent rules? Base of 2, because that's what I'm multiplying. How many 2's do we have? 12. So 2 to the 12th power. Okay. Choose how you want to go about doing this. To enter their home, the Clayton family enters a 4-digit code. How many different codes are possible? Okay, well, we talked about how digits are 10. 4, 10 to the 4th. Okay. Same deal. I think it's like that. Is that right? Yep. Okay. All right, fundamental counting principle. Pretty basic. Factorials. Okay, factorials are new. It looks like that. You're really excited about a factorial because there's an exclamation mark there. Okay. A factorial is written like this. So you might see a factorial like this, 9 with an exclamation point. It is the product of all of the natural numbers. Natural numbers are just whole numbers, okay? Counting from n down to 1. So where we start, and we're just gonna count down. So here's an example. 9 factorial is going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, and then I end up at 1. If I did this in my calculator, I would get 362,880. Okay. 12 factorial would be 12 times 11 times 10 times whatever, right? That's a long way to type that. So, let's talk about how to use our calculator. So I want 12 factorial, that was the problem, so I'm gonna type 12. And then instead of going times 11 times 10, right, I could sit here a long time and do that. Or I could hit 12, hit my math button, and then back to here. Remember, this is where we got abs here when we were doing that unit. Well, over here on the far right says probability. That's where we're gonna be in this unit, probability. Down here, number 4, that's the exclamation point. That's your factorial. So 12 factorial equals that. which is a big number. Where is it? 479. 600. And you can do the same for 8 factorial. Now this one right here, 17 factorial divided by 11 factorial. We can do that in a calculator. We can. We just got to be very careful about how we do it. So the numerator was 17 factorial. Put that in a bubble. Divide that by 11 factorial in a bubble, and then you get your answer, 89, 107, 20. Okay. But let's figure out why. Why does the factorial for that division work like that exactly? And maybe if there's a different way we can think about it. So 17 factorial looks like this. 17 times 16 times 15, blah, 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 times 11 times 10 times 9, blah, 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 times 1. Okay, that's how it works, 17 times 16 times 15 all the way. Well, 11 factorial is 11 times 10 times 9, blah, 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 times 1. So just like normal fractions, what's on the top can cancel with what's on the bottom. I can cancel all of this repeating here. And what I'll be left with in the numerator is ultimately 17 times 16 times 15 times 14 times 13 times 12. Those are the numbers that I didn't cancel all over a 1. And if I multiplied this in my calculator, I would get the same thing that we got with our calculator over there to get the answer. Okay, so that's just one way of looking at that. 0 factorial, you would think 0 factorial, you would think it, because you're like, okay, n starts with 0. Anything times 0 is 0, right? So why does 0 factorial equal 1? Let's check that out. 0 math factorial. Why does it give you 1? Huh. Maybe you do some thinking, maybe you do some digging, figure that out. But 0 factorial is absolutely equal to 1. Okay, a permutation. A permutation is a various amount of combos where order matters. Okay, a permutation can be written as NPR. And we have a formula for it. We will not really use the formula in this class, but I will write it so you have seen it. I don't have this memorized. That's it. And sorry, yeah. This is not a formula I use all the time, so I do not have it memorized because we don't need to. We can use our calculator. N is the total number of objects available, and R is the number of objects to use for our arrangement. So a permutation, if you have it where the number is the same, NPN, that's the same thing as saying N factorial. Okay, so now that is out of the way, let's actually see what a permutation matters and an example of where we would use it. How many different ways can you rearrange the letter in the word dinosaur? So here, when I'm rearranging letters, order matters. Because if I choose to rearrange this in a way that the S is first, and then whatever comes after it, right? It doesn't matter. But I can't choose the S again. I've already used it in the first slot. Order is important. I can't just suddenly have a second S at the back end. That'd be weird. Okay, so that's where order matters. Let's not do the formula, and let's do the calculator way. How many different letters do I have to choose from? What is my N? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Are there any repeats? I don't see any repeats. That's good for me. And I want to use all of the letters. I want to use all 8 of them. So here's how we do it in the calculator. I'm gonna hit my n first. My n was 8. So I clear this all out, get rid of it. N is 8. Now, math, back to probability tab. NPR, that's the permutation one right there. I need to put the 8 first because it needs to be in the slot for this n. Now I'm gonna do the permutation part, hit enter. And then my R was also 8. I need to type the 8 first because it goes with the R, and I need to end with my R at the end. And it's going to tell me that I can rearrange dinosaur 40,320 different ways. And this is the exact same if your N and R are the same, just like this. Okay? It's going to be 8 factorial, and it's going to equal the same thing. Okay, 7 students are competing in a geography bee. How many ways can they finish first, second, and third? This is another place where order matters. If a student wins first, they can't win third. So order is important. Once you pick a kid to win first, you can't choose from them anymore. There's only 6 kids to choose from to get second. You choose the second place. Now you only have 5 kids to choose from for third. So the amount of total kids here, n, 7. The amount of kids we are going to choose, 3. Okay, so 7 was my n. Go over to probability, NPR, and I only want 3 of them. Only 3 can place. 210. We can have 210 different winners. And you can write it out like this, 7P3, if you want to write it out like that. Melanie is taking 4 classes, American History, Algebra 2, AP English, and Chem. How many different ways can these 4 classes be arranged on your schedule? Again, order is important. If you have Algebra first hour, you can't take it again 4th hour. So I have 4 classes, that's my N. How many different ways can I take all 4? R is going to be 4. So this is going to be 4P4, which is the same as 4 factorial, because when these letters are the same, you can make it into a factorial. I just happen to know that 4 factorial is 24, but let's go check the calculator to be sure. 4P4. 4 math over, yeah, works out to be the same. And we got 1 more, I believe, or 2 more. 16 players on a baseball team. How many ways can we make a 9-player batting order? There are 16 kiddos, and I can only have 9 of them on the field at one time. 16 P9. 16 P9. Probably a lot. A lot, yeah. Probably a lot of different ways. Okay, I'm not going to write that down in your notes, but the answer is very, very large. There are 28 students. How many ways can a student elect a council representative and an alternate? Okay, so 28 kids and 28. I want a representative and an alternate. I only want 2. So this is going to be 28P2. And this one, I don't think it's going to be very much, because as soon as I pick that first kid, I can't pick them again, but I only need to pick 1 more. Think about it. Think about what this is saying. I have 28 kids I want to choose from. I pick 1. Could be any of them. Could be any of the 28. Once I take that kid out, I only have 27 other kids to choose from. Let's look. 28P2. 756. Is that the same thing as 28 times 27? Yeah. Okay. The reason for that goes back to how the formula works. N was 28. N minus R, 28 minus 2 was 26. 28 factorial over 26 factorial. It was the same thing as this, where we canceled all of the common things on the bottom. So from 26 times 25 times 24, that got canceled in the bottom, just like it got canceled in the top, right here. So I was only left with my 28 and my 27. That's how these things connect. But if that's not sticking, don't worry about it. Calculator, just like that. Now, permutations with repetition. Okay. How many different ways can we arrange the 10-letter word automobile? Okay. It tells you that there's 10 letters. That's going to be my numerator. How many different choices can you choose from? And there's 10 letters. Now we got to check, because it says repetition, there's probably letters that repeat. I see 2 zeros, or 2 O's, I guess, when you're talking about letters. Any other repeats? A-U-T-M-B-I-L-E. I don't see any. Okay, so I don't see any other repeats. It's going to be 10 factorial over 2 factorial. Let's do in our calculator. If we're going to do this, we're going to make sure we need to use bubbles. 10 factorial divided by 2 factorial, which is 2. But for completion's sake, we'll put the factorial there. So you can type it just like you see it. And then there's that many, 1814400. There are that many different ways. So you need to eliminate the repeating ones, and that's what the denominator represents. How many different 9-letter arrangements for this one? Okay, well, I know that there's 9 letters because it told me that. Where are the repeats? I see 2 P's. I see 2 A's. Any other repeats? D-A-S-E-R. No. Okay. So I had each of these represented how many repeats. This was the P's, and there were 2 of them, and this was the A's, and there were 2 of them. If there were 3 A's, well, this would be 3 factorial, but it's not. There's only 2 A's. So we're going to type this in our calculator just like we see it. In a bubble, 9 factorial divided by, and then again in another bubble, 2, oops, nope, not log, 2 factorial times 2 factorial. Okay, keep your parentheses all nice and neat, get an answer, 9720. Now, permutations are when order matters. A combination says order does not matter. And CR stands for choose. And there's again a very complicated formula for this. Oops. And we will not use it. At least I won't. You're free to. Okay. Again, the total number of objects is n. The number we want is r. So your shortcut for, n, choose n, is 1. Okay. How many different ways can you pick? Like if I have 8 kids for an assignment, I want to pick all 8 of them. There's only one way I can pick if order doesn't matter, so I'm going to take them all. There's only one way. I'm going to take all these kids. All right, Natalie. Natalie has 16 close friends. How many ways can she choose? 5 to be bridesmaids in her wedding. 16 friends. She's going to choose 5 of them. Okay. All right. Calculator time. 16 was the n, so it gets typed first. We're going to go math, and we're going to go back to probability, and now this 3, NCR, that's going to be our choose. 16, choose 5. Hit enter, and there's not that many. 4, 3, 6, 8. That's how many different ways she can choose. 24 students in the kindergarten class. How many ways can we choose? 8. 24, C, 8. 24, C, 8. 7, 3, 5, 4, 7, 1. Okay. Abby's adopting kittens. 18 kittens. How many can she choose? 2. 18 kittens. We're choosing 2. 18. Choose 2. 153. 12 employees. How many can we choose? 4. Okay. 85 players. How many can the coach choose? 3. You can do all of those in the exact same way. So here's where I'm going to leave you. I will challenge you to attempt this page on your own. So if you remember that a permutation needs specific order. Order matters. If I pick someone, I can't pick again. A combination says no specific order. Determine whether each of these statements represents a permutation or a combination, and then give an answer. I will do the first one for you. How many different ways can 4 candy bars be chosen? A way that sells 30. It's going to be C. 30. Choose 4. We do that in our calculator. I bet it's a big number. 27405. And then I guess I'll be nice and do the next one for you too. How many different ways can 13 students line up for lunch? Well, we have to think, does order matter there? If I line up first, I can't also be last. So whoever's in first is already taken. Order will matter here. So this is going to be a permutation. And there are 13 kids. That's my N. And all of them need to line up. It's going to be 13P13, which is the same as 13 factorial. And that is a gigantic number that I'm not going to do that you are welcome to do. Okay, good luck.